Hello, everybody. Welcome to today's presentation, The Year in HTRI Research 2020. It was quite a disruptive year last year, but we were able to continue our research uninterrupted, and I'd like to be able to share what our research team learned with you now. What I show here on the screen is a picture of our test bay at our Research and Technology Center. We were able to keep this center open throughout the year and as we continued to collect experimental data. I am Tom Listina. I'm Senior Vice President of Engineering, and I oversee the research group, and I have the privilege to be able to present their work to you today. Our research program focuses on industry trends and then gaps or areas where we need to learn more in the area of process heat transfer. So in the industry trends, the key one is lowering the carbon footprint, but we also assess new technologies. In the gaps in process heat transfer, we focus on predominantly areas of off design. Now, what we show on this slide is the items that are italicized and that are shown in blue are going to be the focus of today's talk. So as far as the trends, we'll talk a little about fouling mitigation and coatings. And as far as gaps in heat transfer, we're going to talk about hard air recirculation of air coolers, entrainment in kettles, non-Newtonian heat transfer, fouling film, and some fouling. The one topic on the gaps that we're not going to talk about is thermosiphon turndown, but we did recently add methods into our latest release of software to address messages on when you might have a turndown condition. API air coolers are very common in the industry to reject heat to ambient. They consist of a bundle of horizontal tubes with high fins, and they require a lot of space. When you are operating in an off-design mode, such as like when the fans might be turned off, or when you have wind and you're getting some recirculation, predicting the performance can be challenging. So hot air recirculation is when hot exhaust air circulates back into the inlet of the same bank of exchangers and warms the inlet flow. Similarly, hot air migration is when hot exhaust air migrates to a neighboring bank and warms the inlet air. Both reduce performance. So the amount or the severity of the recirculation and migration can be related to the recirculation ratio, which is the ratio of the actual inlet temperature minus the ambient air temperature divided by the actual outlet temperature minus the ambient inlet temperature. From that recirculation ratio, you can identify a derating factor called the effectiveness recirculation factor, which is essentially 1 minus that recirculation ratio. It can be used to reduce the effective mean temperature difference or the duty. Now, our study focused on CFD analysis at this point in time. We hope to gather some experimental data in our rig at our facility to help validate some of the results at some future time. But the first part of the study looked at 4 banks of air coolers. And in these banks, what we're looking at is varying the wind speed and the wind direction. So you had a wind direction that's along the long side, in this case it's the z-axis, or you have a wind direction along the short side, or the x-axis. And in the conditions shown here, we're showing the exit air temperatures with a wind velocity of 5 meters per second. Now, what we learned from this parametric study is that we were able to develop a correlation for the recirculation ratio that is a function of the height of the bundles above the ground, the length of the bank, long bank, the separation between the banks of exchangers, the wind velocity, and the wind direction. And what we found was the literature-based correlation from the Cooling Technology Institute may be a bit too conservative. In other words, we are calculating a lower recirculation ratio than we would calculate using their correlation. So with these results, you can do hand rating calculations that can help you optimize either the layout of your bundle, if you know the prevailing wind direction, or you can maybe derate or figure out how to derate your unit if you're operating under certain conditions. We continued the study to look at mitigating measures, and the two mitigating technologies we looked at were windscreens, which can be used to guide the flow better with screens below the fan and the plenum and the bundle, or chimneys, which are installed above the fan bundle and plenum. And what we're showing here, and you can have a combination of chimneys and windscreens. And what we're showing here is the flow paths of the exit air with these various mitigating measures inserted. Now, changing subjects to falling film evaporators. Falling film evaporators are a well-established technology, largely for fluids where you need to evaporate that are temperature sensitive. So an example might be water-based solutions of sugar and glucose, milk products. You don't want to burn the milk if you're making ice cream. Also items such as caustics. They can be used for other chemicals also for mixture separation. And the characteristics of these evaporators is they have a low pressure drop and they are ideal for vacuum service. They have lower temperature differences and the residence time is short. And that's because the liquid and the vapor are flowing in the same direction. And then so there's no liquid holdup. And they generally have low fouling tendencies. Typical configuration is shown here, where you have the feed at the top of the unit and you have a liquid distributor to ensure all the tubes get wet. And the length of the tubes is around 10 meters or so, can be more than that, sometimes less. Tube diameters between 20 and 75 millimeters. And you establish a co-current flow pattern of the liquid from the top of the tube to the bottom, where the vapor is generated as you travel down the tube and accelerates. Common heating medium is steam because it can be used to create a uniform wall temperature. The liquid and the vapor product are then separated at the bottom of the unit. Now, what has happened with falling film evaporators is that there is little data available for the actual configuration where you're evaporating inside of the tubes. A lot of the current methods that are used were based on data where you were vaporizing outside a tube. So we decided we needed to collect significant amount of data to be able to get more accurate correlations. And one of the reasons for the incentive for this work is we've been getting feedback that designers are making these units with higher and higher vapor velocities. And there's concern that you can get some entrainment in the liquid, adverse entrainment. Furthermore, there's concern that because the original validating data was never really based on the proper configuration, there may be a strong conservative bias in the data. And in order to get more accurate answers, we needed to look at that. We have come to know that there's several processes where the actual output of the process depends on the falling film evaporator performance. And so study in this area was considered warranted. So we looked at a variety of fluids, both pure components and mixtures, with a variety of wall superheats from like around 2 degrees C to over 30 degrees C. We have vacuum pressures and then pressures above atmospheric, and a wide range of Reynolds numbers and Prandtl numbers. What we show here in a video that you can barely see the rippling is a video of our test section where we use a weir type of supply system to achieve a liquid film inside the tube. One of the items that we learned about was pressure drop, and we learned that you needed to base frictional pressure drop based on the flow regime. What we show in this particular diagram is a graph of friction factor versus vapor Reynolds number. And in this graph, you clearly can see that the trend of the friction factor changes depending on the flow regime. The previous model that we have used for friction factor did not show this transition based on this flow regime. Another area or another lesson learned in this study that we have done was that vapor shear greatly enhances heat transfer. Therefore, we were able to confirm indeed that existing correlations are quite conservative, particularly as you go into lower vacuum and higher vapor velocities. What is shown on this particular graph is a ratio of the calculated heat transfer coefficient divided by the measured one for two different fluids, for paraxylene and ethylene glycol. And it's as a function of the Weber number. The Weber number is a non-dimensional number which looks at the slip, or the difference between the vapor and liquid velocities. And then it also has the liquid film thickness and the surface tension and the vapor density. And it clearly shows as the slip increases and vapor velocity increases, the existing or the older calculational methods are greatly conservative because there is this enhancement. The vapor shear tends to press and make the liquid film thinner, and that results in an underprediction in the heat transfer coefficient. Both of these items, pressure drop and heat transfer, are now folding into a process by which we are looking to upgrade our software. Now moving on to Newtonian fluids. So Newtonian fluids, in a way, are an artifact of the Navier-Stokes equation. And they are an idealized behavior where the shear stress is directly related to the strain rate. It's a straight linear relationship as shown. It works pretty good for a wide range of fluids, but it's really idealized for all fluids. And so there are other fluids or non-Newtonian that have different behaviors. There's the class of fluids called the power law fluids. One of them is a pseudoplastic or shear thinning fluid. In a shear thinning fluid, after you get the fluid moving, its apparent viscosity decreases. And then there is a dilatant fluid. In that case, after you get the fluid flowing, it shows an increase in apparent viscosity. But there are other types of non-Newtonian behaviors. There's viscoelastic, there's time dependencies, and then there's observations of like a yield stress. You have to apply a large force just to get the fluid to move. So these pseudoplastic or shear thinning fluids have a wide industrial application. You see them a lot in food and chemical industry. And usually you process them or heat them in laminar flow. And so therefore they have a high apparent viscosity. They're described by the equation shown there, where you have a power law applied to the strain rate. Currently, our plate frame heat exchanger program, XPHE, has an apparent viscosity power law model. But we did a survey of our members and found that they really want to have shell and tube ability for non-Newtonian service. So that was one of the incentives behind this study, is to gain some real data to help do the models more accurately. And indeed, we learned that. We tested ketchup in our tubeside single phase unit. The picture shown there shows the progressive cavity pump in that particular unit. Our progressive cavity pump is very, very helpful at being able to process slurry flows and high viscosity fluids. And in order to understand or to reduce the data into methods, we used an incremental model that we developed in Python. And what we learned is that if you were going to predict heat transfer with standard Newtonian type correlations, in other words, standard correlations that are used today with Newtonian apparent viscosities, you underpredict performance by quite a lot. And this plot here shows you that that is to be expected. What we have on this plot is you have the velocity profile as you cross the cross section of a tube. And for a Newtonian fluid, n is equal to 1, and you have the classic in laminar flow, you have a classic parabolic profile. For a shear thinning fluid or pseudoplastic fluid, you have n is less than 1, in this case 0.1, and you can see that the velocity near the wall is higher than what you would predict based on the Newtonian assumption. Therefore, it's not surprising that you get higher heat transfer than predicted by that, because you have better shearing near the wall. Now we move to kettles. Kettles remain of high interest to industry, but they're also challenging to model. What we show here in this diagram is a U-tube kettle where the liquid level above the bundle is maintained with a weir. And the areas that are challenging when you do thermal analysis are, one is the recirculation, where the liquid that does not vaporize tends to recirculate back to the bottom of the bundle and mixes with the feed. Above the liquid level, you have a froth that can form and then entrained liquid that can escape the kettle. In general, you do not want to have a large amount of liquid entrainment. We did a study looking at entrainment this past year, and that was based on a geometry, a BKU TEMA geometry for propane vaporizer. And what we show in this diagram is we show that it's not uniform vaporization, and virtually half of the propane is vaporized at that red vertical line. And then we also show that the nozzle is not directly placed over the 50% vaporization point, which is common. Wanted to see what effect that would have. When we look at the tube layout, you notice that the liquid level is maintained pretty close to the top of the tube bundle with a nominal froth that is assumed. Now our software XIST does entrainment calculations based on a long history of our research in the area. And a couple of things come out when you look at the results. In the plot on the left, you can see that the vapor velocity is not uniform along the bundle length. XIST calculates that and accounts for that. In the center plot, you see the entrainment ratio as a function of the kettle diameter. And of interest in that particular figure is that if the kettle diameter was smaller than the current sizing basis, you can get a very asymptotic style of entrainment ratio. We wanted to investigate that further. And finally, for the plot on the right, what we show there is how much entrainment would we expect for different froth levels. Now, the default froth level is like 127 millimeters in XIST, and we challenged that. Is it really that value? And we had some very interesting results. One of the results was the sensitivity of the entrainment to the froth level assumption. So what we're showing here in the colorful diagram is we are showing the volume fraction of vapor at different locations in the bundle. The full red version is all vapor, but as you get a little bit of orange, you have some liquid entrained. And what you notice there is at the level of 1474 millimeters, there seems to be a level that can be drawn there where it's largely vapor above it and a lot of two-phase below it. And we notice that the entrainment predicted by CFD result matches with the XIST calculations if the froth level was assumed to be that elevation. The XIST result predicts a much lower amount of entrainment, but it's based on the default 127 millimeter froth height. This result is not necessarily conclusive, but warrants further investigation, which we are doing now. Similarly, we looked at how entrainment increases as you decrease kettle size. And as I indicated before, and what is shown here, we have entrainment ratio versus kettle diameter, is that XIST predicts an asymptotic behavior in the entrainment ratio as your kettle diameter gets near 1700 millimeters. The CFD results do not necessarily support that asymptotic behavior. Also, an area for further investigation. The plots to the left show the vapor volume fraction for the various calculations that were shown in the graph on the right. Now we move to coatings. So what is the incentive that we want to study coatings? In the past, the lifespan of a heat exchanger could be increased if you were able to protect the metal surface. And that was an incentive to study coatings maybe 30 years ago. But now we're seeing that there's more interest in coatings either to mitigate fouling or improve performance. This is related to the lower carbon footprint and also related to the money benefit that you can get for improved performance. It's those items 2 and 3 which are well suited for HTRI study. So we're taking a look at that. And what we found is there are a lot of commercial coatings out there. There is basically an explosion in the number of companies that provide different types of coatings for different functions. Now, coatings very often are classified by the binder material, epoxy, fluoropolymer. But the fillers are very, very important. And the fillers can either increase the thermal conductivity, can control the viscosity, can add antimicrobial attributes. So just trying to get your understanding around the many types of coatings, it's important to try to classify them. So they're also a function of surface modifications. And so a traditional coating has a direct deposition. But a newer term that is used is a surface functionalization, which might modify only a couple of atoms thick, a nano style of interaction, changes the surface energy for a specific desired functional attribute. It's those two areas that are areas of our study right now. The third area of structured surfaces is of interest to us, but is outside the area of our particular project. These structured surfaces are actually structures at the surface that give you a desired functional attribute. In this case, what we're showing here is condensing droplets that jump from the surface. So there's many attributes that we're interested in. There's the adhesion attribute, and there's a lot of open literature standards to look at that. There's also durability issues related to abrasion wear, like can you run cleaning equipment over the heat transfer surface. But then you move into the area where HTRI really provides a lot of insight, and that's in the thermal resistance and this notion of hydrophobicity or oleophobicity related to condensation mechanisms. Hydrophobicity is related to steam condensation, and oleophobicity is related to oils and that sort of fluid. So where HTRI can provide value is really providing a bridge between what is studied in academia and industry and vendors. We can tie the various elements together and provide useful and practical guidance to our members. Now I'm moving over to our crude oil filing program. And we have a long-standing, I guess you could say, brand in studying filing and crude oil. Our crude oil filing program now is, I think, 25 years uninterrupted research. And the various goals of the program are to collect the best-in-class data, to be able to predict the fouling. And the fouling prediction is related to not just predicting how quickly a unit will foul, but also what sorts of chemical processes affect the propensity to foul. And we want to be able to link it to the chemistry. We also want to be able to describe how you can use the data that we collect in our research into a refinery. And finally, we want to study ways that you can mitigate fouling. In the past year, we upgraded one of our 3 crude oil filing rigs. And now this HTFU1, as we call it, has 6 test sections. That allows us to collect a lot more data for the extended time it takes to run a filing test. Our standard filing test runs about 1 month. Right now, we're looking at a variety of factors that can impact filing of tube diameter, particle size, flow rates, bulk temperatures. And the advantage of having 6 test sections should be obvious. You can look at many more variables in a parametric fashion. And the diagram here shows the new upgraded set of test sections. So fouling models is an area of great interest, and it's an elusive area to get a universal fouling model. So we have been collecting our recent set of data in the 3 rigs starting back in 2010, and we've been generating a library of this data. We are starting to analyze the data systematically and ranking it, reconciling it, and being able to determine, and we've also in the process of doing this gotten more and more accurate measurement techniques. Looking forward, we want to come up with modeling methods for this data, whether they be like a neural net type model or a more traditional model, and then we want to be able to link it with chemistry data. Focus of the recent studies in the past year are looking at flow parameters and how they're related to performance. So what we show here is pressure drop and fouling resistance on a plot of roughness versus thickness. And so pressure drop increases both with roughness and thickness as you would expect. And it's actually a fairly sensitive indicator, which is good. However, fouling resistance or thermal performance has a little different behavior. Fouling resistance increases as you increase thickness. However, at a given thickness, fouling resistance decreases as you increase roughness. This makes the study of fouling behavior, as it is a transient sort of phenomena, interesting because you can have increasing and decreasing fouling resistances with time. Similarly, you can look at the plot a little differently. In this case, we have Reynolds number and shear stress as a function of bulk temperature and mass flow rate. And Reynolds number is like a measure of how you can convect or move the fouling components to the wall surface. And as expected, it increases with mass flow rate, but also increases with bulk temperature. Shear stress, on the other hand, is largely just a function of mass flow rate and not temperature. It's fairly sensitive to the velocity. So looking ahead in 2021, where we are now, these accomplishments we had over last year, some of them are moving into our software, and that is our guidance for hot air recirculation. We are looking to replace the falling film evaporator methods, and we're introducing new non-Newtonian heat transfer methods. We need to complete this kettle entrainment study and get a coatings guidebook out to our members. But another interesting study this year that we are taking on is a more open study by the Rapid Institute. And the Rapid Institute stands for Rapid Advancement in Process Intensification Deployment. And it's a center of excellence that's looking at ways to intensify process industry. And heat transfer is a central area in that. And we are contracted right now to be able to do a demonstration test that we're going to be able to report on to everybody. It will be open literature. And the test that we're planning to demonstrate is one where we are going to be putting 2 advanced or over the horizon type of technologies into a brazed plate fin air cooler. One of the technologies is the fluttering reeds, and these fluttering reeds provide for enhancement of the heat transfer without a significant increase in pressure drop. And then we're also looking at the same time in an acoustic dispersion technique. And acoustic dispersion technique will be able to increase mixture condensation, maybe shorten the length of tubes, because you can better mix the liquid and the vapor phases. And they are both shown with pictures shown here. Our partners on this project are the Georgia Institute of Technology and University of Illinois. So those results will be made public and are a very high visibility project that we're excited to be able to do. And that's really what I had for this particular presentation. If you have any questions, you can send them into support. We can provide more information. And I encourage you to look for some more of our upcoming events.